Welcome back. Just learning about how positive derivatives mean that a graph is increasing and negative derivatives mean that a graph is decreasing. And we're going to talk a little bit about how this can help us find local maximums and minimums. So let's think about this for a second. We've got something called the first derivative test, and I bet you can figure this out on your own. If my first derivative is going from a positive to a negative, what does that look like and what does that tell you? So I'm going to really quickly sketch this. Okay, I'm increasing, and then at some point I stop increasing and I start decreasing. Right? So I went from a positive derivative to a negative derivative, increasing to decreasing. Well, at that point when I changed, what's happening? I'm right at the top of some kind of a hill. Okay, so this is telling me that this should be a local max. A local maximum. It's local because it doesn't tell me anything about what happens later on. Maybe there's another bigger maximum. So at least nearby it is at a maximum, a local max. Similarly, if we think about, okay, oops, I need to fix this a little bit. If I went from a negative to a positive, then what's happening? Well, it means I'm going down, and then I start going up, which means at least nearby I'm at some kind of a local minimum. I'm at as low as I go, so this is going to be a local min. And that's really the first derivative test. It says, hey, if your first derivative switches signs, then you're at some kind of a local max or min, because you've switched from going down to going up, or going up to going down. This is shockingly powerful. Very, very often in math, we want to figure out the best way to do something, the fastest way, the most profit, the least time. And this is all a matter of finding local maximums and minimums. And so using derivatives to either help us get closer by going down to lower and lower values, or to actually tell us that we are at the lowest possible, is crucial in a lot of jobs that make you a lot of money and are really important in the world, right? That's how you optimize and how you find the best way to do things, is with math and really using things like the first derivative test and this behavior. Okay, tangent done. Let's go ahead and look at this last case. If I go from positive to positive or negative to negative, what is that telling us? And what would that even look like? Well, maybe I'm going something like this. So this is x cubed, looks like that. Or even say, how about negative tangent, looks like that too. Where it is actually flat, it is 0. Right there or right there. Okay, but notice it's not a max or a min. It's like I paused for a second, but it wasn't even a second. It was an instant, right? It wasn't even a measurable amount of time. And so this is just neither. I can have a 0 in my derivative without having a max or a min. It's really that change in signs. Neat. All right, example time. Let's use the same example as above and take a look at what's happening in that graph. So it looks like I went from a minus to a plus, to a minus to a plus. And so right away, just in this little sign chart here, this tells me that f has a local max at, well, I went from a positive to a negative at 0. Okay, and a local min at negative to positive, down to up, looks like negative 1, and negative positive looks like and 2. Okay, quick aside here, oftentimes if it says at, they mean what's the x value. It is also okay to give the x and the y values as a point. I didn't want to compute the y values here that fast, but if we did, we'd want to plug in the 0 into the whole function, not the derivative. So we could also write that this is at the point 0 comma 5 is what I get if I plug it into f, not f prime, right? Because we're talking about f. F prime is just how we got that information. Okay. Similarly, I could plug in negative 1 or negative 2 into f to figure out what is the y values. Okay, so at, we're saying, oh, it's a min at. That's usually going to mean what's the x value a minimum of would tell you the y value. And sometimes if you're unsure, just give the whole point, like 0.5. I'm not too worried about the details of the English language in this case. Very, very neat. Let's do another one that maybe looks a little different. I'm going to go ahead and use a trigonometric function. So depending on the order that you are learning this course, this may be a bit new, and otherwise you should practice your trig functions. So let's work through this. G of x is x plus 2 cosine of x, and I want to find all the local max and min on a given interval, negative pi over 2 to 3 pi over 2. So what do I got to do? Well, what do we tend to do in this class? We take derivatives. Let's go ahead and do it. Looks like g prime of x is equal to, we can do these one at a time because of our derivative rules. So the derivative of x is a 1 plus, that 2 hangs out, and the derivative of cosine is, whether you know it or not, negative sine of x. Very neat. Okay, that's it. That's the calculus part. Now it's really a matter of knowing what this means and how to do our pre-calculus. Let's clean this up a little bit. 1 minus 2 sine of x looks a little bit prettier. All right, we want to know, when does this equal 0? Because we want to know, when is it positive or negative. So 1 minus 2 sine of x equals 0. Do you know how to solve this? Let's solve for sine of x. So this becomes, if I bring the 1 over, 2 sine of x negative 2 sine of x equals negative 1, and then I divide through and I say sine of x equals a half. Very nice. There's two things we could do from here at this point. We could either apply an inverse sine. That's how you get that x out of sine of x. And then you're going to have to make sure that inverse sine is going to give you one value, but you have to make sure you get all of the values in that interval. Okay. Or we could maybe remember our unit circle, also a good option, and say, all right, when is sine of x equal to a half? Okay. So my sine starts off at 0 It has a maximum of 1 up here at pi over 2, and it's going to be a half, actually, right here at pi over 6, but also right here. Right, sines are the y values as you go around. Cosines are the x values as you go around. So it looks like this angle right here is what we want. So when x equals pi over 6, but also over here. So this value over here is, we're at pi, and so this would be pi minus pi over 6 is 5 pi over 6. Let's do a quick check and say, are we in our interval? Negative pi over 2 is down here. So all my y values are negative all the way down to negative pi over 2, so it's not going to be any of those. My y values are positive in here, and then all the way to 3 pi over 2. So we don't need to worry about that quadrant at all. It really is just these two values. Okay. Yep, so that's them. Those are the only two I need to worry about. Just as a quick trig reminder, my sine values, usually there's 3 we worry about. So it goes 1/2, it goes root 2 over 2, root 3 over 2, and then 1. And those are in order increasing, 0 all the way up to 1, and then they work their way down, and then they get negative when we get on the bottom side there. Okay, so these are the two we want. If I went to try to make a number line like before, we would get this. We'd get a pi over 6. We'd get a 5 pi over 6. We have a 0 here and a 0 here. If I were to plug in 0, I would get oh, we got to go back to our derivative function up here, right? We want to know, sorry, I had a moment there. If we go back to this derivative function, and if we plug in a 0, it looks like we get a 1, which is positive. if we plug in maybe a number in between, like pi over 2 into this derivative function, sine of pi over 2, that's at the very top of that unit circle, right? 0, pi over 2, pi. That would give us a 1, because that's the y value. So I'd get a negative 1 there. So it's a minus at pi over 2. And then you might guess if I plug in 5 pi over 6, right? Sorry, if I plug in pi, that's a better choice, then I would get just a 1 again. So it's going to go plus, minus, plus. All right, which means that our local max is at well, we go from a plus to a minus at pi over 6, and a local min at 5 pi over 6. Going from a minus to a plus. Definitely take a minute, draw a few graphs, make sure that this makes sense to you on the graphs themselves. Use a graphing calculator, use an online program like Desmos. But if I was going to graph something like x times 2 cosine x, it looks a little funky. It looks kind of like this, right? Because it looks like a cosine of x, which is a little smoother than what I drew, but that x is making it bigger and bigger and bigger. Meanwhile, 1 minus 2 sine x looks more like a trig function. Okay, so what we're picking out here is these little hills along the way that happen to be in my domain. The domain is going to cut this off. But also take a second and graph 1 minus 2 sine of x and make sure that it is agreeing with what you're getting as well. Graphing calculators can really help you check your work and gain some intuition here, or use a computer to graph it. It takes a long time, I think, to get sorted in your head. Here's this function, and here's its derivative, and they look different, but they're talking to each other. They're giving you information about each other. So keeping track of like, oh, I just care about where this thing is positive or negative, but I care about where this thing is growing, where it's increasing. All right, pretty neat. Next up is our second derivative.